All right, here, let's do part 2 of the test, and these are the free response here. And so starting with number 25, it says here, a ball is dropped from rest. Neglecting air friction, how far does it fall in 10 seconds? All right, so I think the best way to approach this one is, again, distance equals, and I'll put this symbol for average speed. And in fact, let me just come over here, because to get the average speed, I have to take the starting speed, which is 0, because it says dropped from rest, and then after 10 seconds. And we could then just say speed equals acceleration times time. That would certainly work. In fact, maybe I'll just do that. If I round the acceleration to 10, because it's free fall, and I go 10 seconds, I get 100 meters per second it's going. Or I could just count it out, because I know it changes by 10 every second. So after 1 second, it's 10. 2 seconds, it's 20, 30, 40, 50, 60, 70, 80, 90, 100. So if I take 100, divide that by 2, I get an average speed of 50. So I'll put over here 50 meters per second on average for 10 seconds, coming up with 500 meters. So there's the one way of doing it. But since it started from rest, the equation distance equals 1/2 AT squared would also work. And so the numbers would look like this. I'd put a 1/2, and if I just kind of round the 9.8 to a 10, and then put 10 seconds and square that, again, 10 squared is 100, times another 10 is 1,000. Half of that is 500. So this would be 500 meters. So either way works. The one thing that don't do is just get the speed and stop. That would be very tempting, because it says how far, but sometimes people read that as how fast, and they answer, this part of it. They do like half of it. Now, 26 is almost an identical problem, except you don't start at 0 speed, so you can't do that. So if you did this equation on 25, fine. Just don't do it on 26. And so 26 would be kind of the same thing, where the average speed would be starting at 17, increasing to 25, and divide by 2. And so what does that come out to be? 30, 40, 2 divided by 2 then is 21. So the average speed is 21 meters per second, and they said it traveled then for 4 seconds. And so 4 times 20 is 80, and 4 times 1 is 4. So that's going to be 84 meters. Maybe I'll put a little box around it. All right. So 500 for number 25 and 84 for number 26. And so you can see those two are really right out of chapter 2. And then these next two are right out of chapter 3 here. They have to do with Newton's second law. It says here a push of 550 newtons is required to move a 150 kilogram barrel across the garage floor at a constant speed. So if this is maybe the garage floor, and here's the barrel, and you push it 550, I'll call that F. That's your push. Whoops, I went off the screen there. That's your push. But the key here, and you might remember this in the review, that there's an important giveaway here. It says here to move it across the floor at a constant speed. So that would tell me, and I'll do a little f for that there is a corresponding friction of 550. So that's how the net force comes out to be 0. That's why it would go across at a constant speed. And so that first sentence is really kind of giving away what the frictional force is. Because then the problem really begins when it says how much push would be needed to then accelerate the barrel at 2 meters per second. So if we go to Newton's second law and say net force equals to ma, here we have a mass of 150 kilograms, and an acceleration of 2 meters per second squared, and so 150 times 2 is 300 newtons. Now, as I warned in the review, don't stop there. That is not the individual push. That is the net force. So the net force then would be, coming back to this picture, how much you push then minus the friction. So that's what I want to know, how much I push, and then minus the friction, which we've already learned was 550. And so this net force we just did, that's 300 newtons. And this is 550 newtons. I should have put a newtons there. So that's telling me that the force I would have to push would be 850 newtons. And hopefully that, again, makes sense, because if I push with 850, and then I'm trying to overcome a friction of 550, you subtract that, leaves me with a net of 300. And 300 then divided by 150 gives me an acceleration of 2. So I'll say it again. Be real careful. Don't stop here. This is the net force. It's not the force you would be pushing. It's not an individual force. The two individual forces, the force you push and the friction, gives you that 300, that net force. That's why it was so important back here to find out what that friction was, so that you could then go ahead and say, okay, I know this one and I know that one, and now I can find what is the push I have to do. So there's the key, Newton's second law, plus understanding net force. Also Newton's first law, knowing then that the frictional force would have to be 150. And really the same thing is here for the skydiver. Here we have a skydiver. The skydiver has a mass of 75 kilograms. The skydiver is accelerating at 3 meters per second as she falls. And so if you take Newton's second law and you put in her mass of 75 kilograms and you multiply by acceleration of 3, let's see, 3 times 70 is 21 newtons, and 3 times 5 is 15, and so we're looking at 225 newtons for the net force. Okay, so again, we're saying this is the net force. So don't stop. In fact, maybe a free body diagram might be useful here. And so maybe I'll just kind of imagine this skydiver here getting pulled down by the weight of the skydiver and then the air resistance here. I'll just put little f. But that's the individual force they're asking. What is the force of the air resistance? So again, if you stop here, you've only done half the problem. You found the net force. So you have to continue on here to say, okay, well, now the net force is her weight pulling her down minus the frictional force. And that's what I'm after. And I've done this one, 225. And then this one maybe ends up a little harder than that one, because how do you do weight? Well, that's mg. And so if you take her mass of 75, and again, we just round g to a 10, that's 750 newtons there. And so I guess the final step would be to move the frictional force or the air resistance to this side and then move this negative to the other one. So if you take 25 away from that 50, you get 25, and you take a 7 minus a 2, you get 525. So there's the individual force. In other words, gravity is pulling you down at 750. The air resistance would be pushing back on you, lifting you up really at 725. So if you subtract the two, you get a net force of 225. And it's a net force of 225. When you divide it by 75 kilograms, would give you an acceleration of 3. So again, warning, don't stop at net force there. Go all the way to the individual force. So again, those two are from chapter 3. And the next one is from chapter 4, and I think the next two are. We'll have to see on the next page here. But here it has a football is kicked, so I'll make a little football here. And so here's my, should give myself more room. So there's my football. And the football is kicked. And they say it's kicked so that it has a horizontal speed of 12 meters per second. And it has an upward speed of, oh, I wrote over the top of that, 30 meters per second. And then it says, what is the vertical and the horizontal speeds of the football 2 seconds later? So there's a speed horizontal and a speed vertical for this problem. Okay, I'll start with the horizontal. We could make a whole chart like we were doing in class, but I think this one's a little easier than that because hopefully one of the things you got out of the horizontal is there's no acceleration. So if it starts off with 12, a second later it still has 12, a second after that it still has 12, and after that it still has 12, and it still has 12. So the half the answer is the horizontal speed is still 12. Now the other half of the answer is the vertical speed, and that's the one that changes by 10. And of course, whether it's slowing down or speeding up, depending on which direction it's going, and this one is being kicked upward here. Upward. There's the upward. All right, so I put a 30 there. So a second later, it would have lost 10, so that's 20. A second after that, it would be down to 10. So there's the two answers, the horizontal and the vertical speed. And that was the whole point of our Motion in Space, our chapter 4, was to show that the horizontal and vertical speeds acted separately, and we would calculate them separately here. And so that's exactly what I've done. In fact, I'll use that here because number 30 is a continuation then of number 29. It says, using the information from problem number 29, find that horizontal distance. And again, if you remember me saying this back in the lecture, the nice thing about chapter 4 is once we learn that the horizontal and vertical speeds are separate, we really just have to go back to chapter 2, where we could do our one-dimensional motion. We would just have to do it twice. And so these problems up here involving distance that I just did once, I'm just going to repeat right here. And so number 30 is really kind of the same as 25 and 26. I'll just take my average horizontal speed multiplied by time. And of course, what's nice about the horizontal one is the average speed is always 12. It started with 12. A second later, it has 12. A second after that, which is 2 seconds, it has 12. And then 3 seconds, it has 12. And it always has 12. Okay, so if it's 2 seconds into its travel, we just get 24 meters. So that's half the problem. How far is it away? So how far is it horizontally? And the other half of this is how far is it vertically? And it's the same idea. I'm just going to put here the average vertical speed during those 2 seconds. So again, you get average by taking the initial speeds, which we said was 30, and 2 seconds later, it's now 10. So add those two together and divide them by 2. That's going to be your average speed for 2 seconds. And so 30 plus 10 is 40, divided by 2 is 20. So this is 20 meters per second for 2 seconds. And so 20 times 2 then is 40 meters. So again, there's my two answers. It's 40 meters in the air. Looks like it's still going up, so it's going to continue to go a little bit higher. In fact, we've done this one before with a speed of 3, and we see that it ends up going a total of 45 before it starts coming down. But it's not asking for those. It's just a simpler one 2 seconds later. So it's gone 12 and then 12 more. And like I said, 1 second more. So after 3 seconds, it's going to be at its maximum at 45. And then this will be at 36. And then it's all going to repeat on the way down. So 36 and 36 would be 72. So it's going to go horizontally 72 meters before the football comes down. So this is a long punt. Maybe unrealistic too. I don't know if those are reasonable numbers or not. But continuing on, we go to the next chapter here. Oh no, this looks like it's also motion in space, because motion in space not only had projectiles, but it all had things going in a circle. And this is more of a plug and chug. It just says, what is the centripetal force? And so if we put together F equals ma, and then we say A is the centripetal acceleration, since it's going in a circle, that's the v squared over r. All we have to do now is put in the mass and the square of the speed and the radius. Sadly, and some of you emailed me, I got careless here. And so for an answer, I'll take 50,000 or 5,000, however you want to interpret that. It was meant to be 5,000, so in the solutions here, I will start off with 5,000. 50,000 is way too much for a car. Actually, 5,000 is a big car. Most of your big SUVs are about half that. So this is a a working truck. Yeah, well, it's a 10-ton truck. That's what it is. This is a 10-ton truck. This is a work truck. Here's our 5,000 kilograms. And then the speed is 25 meters per second, and we would square that. And the radius is 50 meters. And maybe I'll start with the units, but hopefully it's one we've done before. Here's the kilogram. This would be meters squared, but there's a meters to cancel, so it's just, at this point, kilograms and meters over seconds squared, and that is a Newton, as it should. And on this one, I'm going to need my calculator here, so I'll take the 5,000 and multiply it by the 25 squared and divide it by the 50 and get, looks like 62,500 newtons is the amount of force. And, of course, if you do interpret this as 50,000, which is 10 times bigger, then your force is going to come out to be 10 times bigger. And so if you did the 50,000 kilograms for the mass and got the 625,000 newtons, that's fine too. That's just my bad on my typo. Then we get to the chapter 5 on the universal law of gravity. Here just says what's the gravitational force between, and I just picked the Earth and the Moon. And so hopefully your first step was to write out, this was what I called the short chapter, in the sense that, hey, there's just one new principle. Now, some of these problems could have been hard. I didn't give you a hard one, but some of them are hard because you start there, but you have to go back to your other stuff, like the centripetal acceleration, if you want to know the speed, like we did in class, the speed of the International Space Station. But this problem doesn't go that far. It just asks for the force. So it's more of a plug and chug here. And they give you the mass of each of them. G's not given, but it's something that probably you should commit to memory, but I know there's a lot of things to commit to memory, and sometimes that can just clutter your brain cells. But in this case, it's open book, so hopefully you just knew what that was, including the units here. And so there's the universal gravitational constant. But again, since it's universal, this is the ones that I think are important to memorize, the ones that are universal for all the physics. Whereas the mass of the individual planets isn't. Although maybe Earth might be an exception to that, but they're probably not worth memorizing the mass of the Earth. And it's given here. And I would say definitely not worth memorizing the mass of the Moon. I don't have that one memorized. I do have the Earth, but I don't have the Moon. And then the distance between them, again, not overwhelmingly important, but that's kind of a common one. And I have it memorized in miles, so I have to convert it into meters, and that's fine. But of course, I am a little bit on the old school in that. That's how I learned it when I was in school. We learned it in miles, not in meters, and so I'd committed that to memory way back when the dinosaurs were still walking around on the Earth. Okay, so now if I put this into my calculator here, 6.67 times 10 to the negative 11 times 5.98 times 10 to the plus 24, almost put a minus there. And then another times 7.36 times 10 to the 22. Oh, I shouldn't have put enter, but oh well, hit enter. And then divided by 3.84 times 10 to the 8th, and that whole quantity squared comes up to be 1.99. Put it on the screen so you can see it, but times 10 to the 20th. times 10 to the 20th. And then looking at the units, the meter squared would cancel here, the kilogram squared would cancel there, and you would, of course, be left with newtons. And so, sure enough, there's the force. And I only gave one there because I ended up giving 3 from chapter 4, since we had the 2 projectile ones, and I thought I'd throw a circle one in there. It's only 1 gravitational one. And then finally 2 more, and we'll be done with the test here, but these 2 are on chapter 6 and momentum. And of course the big key is that hopefully I got this across and it worked well having a chart here. So I'll just start off my chart here before I read it. But if you have 2 things that are interacting, no matter how they interact, big or fast or small or slow or old or new or blue or whatever, the momentum before the interaction is equal to the momentum after the interaction. Now, you do have to be careful. You make sure you include all the objects. In this case, there's 2 of them because it says here a 3-kilogram ball of soft clay is thrown at a 5-kilogram cart. If the clay and the cart stick together and travel at a speed of 2 meters per second, at what speed did the clay hit the cart? Okay, so in this problem, if there's anything that's going to make it hard, it might be the fact that they don't give you the initial speeds, they give you the final speeds. So we know more about the after the collision than we do the before. So I'll write out afterwards before. So they stick together, the ball of clay, the 3-kilogram ball of clay, then goes moving with a speed of 2 meters per second. But also it stuck to the cart. So the clay, stuck to the cart and they both go moving. So that would tell me then that the cart is also moving with a speed of 2. And so this is 10 and that's 6. And so we're talking about 16 units of momentum. And that's afterwards. So we know that has to equal 2 before. Now, the before then would look something like this. We would have the 3 kilograms from the ball of clay thrown at some unknown speed. That's the question. What is the speed? Now, the other one is stationary, so that would be 0 speed, which is 0 momentum. So this is equal to 3 kilograms times v. And so just to give me some room here, then I would finish this by saying, okay, so v is, and I guess I would cancel off the kilograms there. And then, oops, kilograms, not the 16. And then the 16 would be divided by 3. So that would be 5 1/3 meters per second. I think, let's see, 3 goes into 15.5 and then 1 left over. Okay, yeah. So 5 and 1/3 would be the speed. And of course, then this one too is a momentum one. There's an interaction. In this case, it's 2 football players. Here is the first football player. 100 kilograms is running at 5 meters per second. It's hit head-on by a defensive tackle that weighs 175 kilograms and is moving towards the quarterback with 3. So the defensive tackle weighs more but is moving at a lower speed. And if there's anything that makes this one hard, it's remembering that momentum is not just mv, but it's a vector. It has direction. So if we say the quarterback is running in the positive direction, we would say this is the 100 kilograms with a speed of 5 meters per second. And the other one, the other object, is going in the other direction. So this is 175 kilograms. Oops, kind of ran out of room there. Negative 3 meters per second to get the total momentum before the collision. So this is 500 units of momentum minus, and 3 times 100 is 300, and then 225? Did I say that right? So that's 525 units of momentum. And I'll just put the units of momentum one time. And so, let me jump over to here. And so 500 minus 525 is not 0, but pretty close. And it's a negative 25. So the defensive player, although running at a lower speed, because of the larger mass, is going to have more momentum, just barely. And so when these two come together, so here's the quarterback going this way, and here's the defensive tackle going this way, and they hit, they're going to be going just a little bit in the negative direction because they're just a little bit more momentum. So they're not going to just kind of stop, and they're certainly not going to go in that direction. That's what would happen if the quarterback had more momentum. The defensive tackle has a little bit, so they're going to go boom and back just a little bit. Which is why then the other side of the equation, we would do something like this. On this side of the equation, we would have the 100 kilograms for the quarterback moving at some speed after the collision, and then the mass then of the defensive tackle going with that same speed. So they stuck together. So just like in 33 and many of the examples I gave in the lecture, they stick together, and that's a clue to say we know their speed is the same. This time we knew they were the same at 2. In this one, we just know they're the same, and that's what we're looking for. It says when they hit and stick together, what is the speed and direction of the two players? And we really already answered the direction. So the direction is negative, or put another way, the direction they are going to move is the direction that the defensive tackle was originally running. Or you could say it's opposite of the direction that the quarterback was originally running. However you want to phrase it, that's the direction. And then the speed is not going to be much, as we see here. But if we put those two numbers together, let's see, this comes out to be 275 kilograms times that unknown speed. So the kilograms will cancel, and I will get meters per second for that final speed. Then I can grab my calculator and put in a negative 25 and divide it by 275, and I get a negative 0.09, or if you just want to put a 1, I'll take that too, but that would be the speed. And again, notice the negative, and not much of a speed, but definitely negative after the 2 hit. And there's the test. And I'm hoping that would be helpful, and the thinking process will train you to be more ready for the next third of the class as we do 2 more weeks of new physics and head into chapter 2.